I'm going to go through the Excel file that says homework with examples. There's another Excel file that just says dynamics homework that is similar, but it has a few different numbers for you to work through as well. This consists of a series of different sets of data to try and analyze and back out. We're going to start with an easier set of data and work our way up to analyzing sets that have errors in that and recognizing difficulties with error propagation and how to clean that kind of a little mess up. Okay, so just starting where we were, this first data set isn't too bad. We have time and position on here, and we're going to go ahead and use this data to find what our velocity is and our acceleration is. Something a little bit different about this data set. We're starting at a position of over 300 and working our way backwards. And so for this data set, that means that we're going to have to find what's the sign for our velocity, what's our acceleration doing. So whether it's positive or negative, you should be able to apply these same equations. Okay, remember for these velocity equations, we're going to need to figure out what our starting velocity is. Now I'm going to guess and just start with 0, and then here my first velocity is going to be equal to 2 times x minus x naught divided by the time difference. Now I have the time set as 0, 1, 2, 3, 4 here, but know that this will work for any kind of random time increment. And then subtract off the previous velocity. And you'll notice that our velocity in this case is negative. And that is because we are moving to the left. Usually positive is moving to the right, negative is moving to the left. So it's like you're backing up. These position numbers are getting smaller. Okay, once we have velocity, we're going to try out acceleration. Again, I'm not starting in the first column, I'm going to start in the second column. And this is going to be just equal to how our velocity is changing divided by how our time is changing. So here's our acceleration, and as you see the velocity go 3, 6, 9, 12, sure enough that looks like -3. At the end of this, we're also going to graph out the results. Looking at numbers is one thing, but really to get a good idea of what's going on, you need to graph it. Insert, and I'm just going to use a regular scatter plot. I'm going to make one graph for position, another graph for velocity. Hold down Control key so that you can highlight these different cells here. So here's our velocity, and you can see that nice straight linear slope, which means we have a constant acceleration for this one. Okay, so this first set of data wasn't too bad, nothing. Just make sure you're familiar with those equations and where they come from, how to make a graph. For all these graphs, you just click on the little plus sign and you get a bunch of options for adding axis titles. For instance, this should be time, and this should be acceleration. You can also click on the numbers and say Format Axis. Let's say I want time to go along the bottom. Then I can say horizontal axis crosses at -3.5 instead of 0. So then I can get a more traditional graph with time along the bottom. So play around with some of those formatting options. There's different options to color your graph as well. Typically just a straight black and white graph is preferred. If this is going to be photocopied, generally everyone just appreciates something a little bit more straightforward. Okay, so there's getting used to making the graphs. Let's go ahead and go down to our next data set. Okay, so read the little comments on here. This next one says, this one is a little trickier. See if you can figure out what's going on. Now we're starting out with just time and position again. That's the same thing we had before. So I'm going to cheat a little bit. I'm going to come up here, Control C, and just copy those equations back down again. Okay, so I've copied those equations down, and same thing, we're going to make some graphs. So here's our position. Not too bad. And let's say Control, and here is our velocity. And uh-oh, something is wrong with our velocity. So we're going to have to figure out what's going on here. And the last one is our acceleration. So again here, I'm going to add a graph. What you're seeing here is some error propagation. And this is something that you'll run across quite often when you're analyzing data. Look at this position curve. It's very smooth, it looks good. There's one little point here at the end that's not quite lined up, but for the most part it looks smooth. Looking at your position data, what should velocity be? Initially, this looks pretty linear, right? Velocity is slope of position, miles per hour, change in position over change in time. So what we should get is a constant velocity, and then the velocity should decrease. If I look at the starting position, so it's the same equations as I had up here. If I zoom in, this is the same thing that we used before. The difference here is if you look at the slope going into this, I'm not starting with a zero slope here. Over here, see how the initial slope of my position curve, it's starting at 0. So we're at rest, and then we're slowly, that slope is slowly getting larger and larger. So this one, we were justified in starting our velocity with 0. But here, the starting slope is not 0, and we're going to have to look at our position data to figure out what it is. So we have 0, 10, 20, 30, 40. That looks to me like a slope of 10. So let's go ahead and change this initial velocity. Okay, so here's our equation. We're changing our initial velocity, and it looks like it should be 10. And there, that cleaned up our graph quite a lot, right? So if you see the zigzaggy stuff, there's two things that are going to cause it. It's going to be your boundary conditions, so your initial velocity, your initial acceleration, initial position. The other thing that's going to mess it up is, if I zoom in on this graph here, do you see this one little data point? I threw in a curveball. There's one data point that's a little bit off. And when you're taking data for your mousetrap car, it's not just going to be one data point that's off. Every single one of your data points is going to be off. But this is just to illustrate the huge mess that's created when everything doesn't line up. So remember, all of the equations that we used here are dependent on change in position over change in time. They're dependent on the slope. And we're just going from one point to the next. So if we have a slope, see how much that one little change in the data changed the slope? So the slope becomes all over the place here. And when the slope is all over the place, that's going to really throw off the velocity calculations. And then, of course, acceleration is from the velocity slope. So now the slope between these 2 points is all over the place. So that means the error is magnified again in our acceleration data. So we're going to have to go back in here and find what point that is and try and clean our data up. And know that for any system, you need to have a physical understanding of what your data should look like. And you might have to do a little bit of detective work to go back and make that work for you. Okay, so we're looking at 1, 2, 3, 4. 4 points back, 1, 2, 3, 4. So that is the little spot that is an error. And if we move this around, so let's say 95.5 instead. That's what it's supposed to be. So that's pretty crazy, right? That just that very little difference, and it wasn't off that much. 92.5 versus 95.5, and that really changed everything around. So that just illustrates some error propagation issues. Okay, so we already have our equations. I'm going to let you see if you can figure out if we start with velocity instead, if you can go back to the other ones. The last thing to do here is we're going to tackle a data set where everything on here is a mess. So let's start by just plotting this position data to see what kind of a mess it is. So insert, and again I'm inserting a scatter plot, and you can see that general curve that you should now recognize that we should get for the mousetrap, but it's not quite smooth, and you're not going to be able to get perfect data for this. Okay, so how should we smooth this thing? Because as it is, if we calculate our velocity from this mess, so let's say we start from rest again, start with a velocity of 0. So here's our velocity from the original data. And we're just going to use that same equation. And we'll do this to see what the original unsmooth data is going to give us. And we can see the mess that's created from error propagation when we have a little bit of a messy data going on. So here's going to be our velocity calculated from the mess. And then what we're going to want to do is somehow clean that up and smooth it out so that we can have a little bit better data on here. Okay, so here's, when you see that zigzaggy up, down, you're looking at some error propagation issues that we're going to have to clean up. What we can do, I'm going to take this data, right-click, say Add Trend Line, and for this one I'm going to use a polynomial. I'll bump this up, even just a third-order polynomial. That isn't too bad right there. So go ahead and do that. Make sure to display equation on chart as you're creating this. And then what I'm going to do is I'm going to use this equation to create a new set of data where my data will follow this nice, smooth polynomial curve. And then I will calculate my velocity not off of the original messy data, but off of this curve. Okay, and I wish there was a better way to copy and paste this equation out of here. So time is what's on our x-axis, so everything in this equation that has an x, I'm going to replace with time. So here's my smooth position data. Y is equal to negative 0.0655 times time cubed plus 1.2633 times time squared. You might have to type this in a couple of times before you get every little thing in there right. This is another reason to only do a third order polynomial instead of fourth or fifth. Okay, so here is that equation, and when you get that equation in right, these numbers should be fairly close to one another. Okay, so 37, 36, 80, 79, right? So they're not perfectly aligned, but they're close. So if I take this position graph, I'm going to just grab the bottom corner here and pull it over. So it's the orange line versus the blue line. So now I'm going to take that orange line and see if I can get a better velocity graph off of this orange line. Okay, so same thing. In fact, maybe I can just pull that equation right over. Yeah, except for the time. So I need to clean up my time. So this is going to be our smooth position data divided by our time this time. And yeah, that's the initial velocity. Okay, so here's the new calculation from the smooth data, and you can see we're still in a little bit of a mess. But remember, there's two different things to clean up your data. It's both smoothing it, and we have to figure out what our initial velocity is. So if I look at this orange curve, I'm not coming in with a slope of 0 here. There's some small slope. So what I can do is just start typing some numbers in. And as I get closer to what that slope is, do you see those wrinkles going away? And really this involves calculus, but it looks like when I hit 3, when I start that velocity from 3, now I have a nice smooth curve going on here. Okay, so this is our velocity data. And the last thing we can do is find our acceleration. And once again, if you calculate the acceleration from that original data that was not cleaned up versus calculate it from the smooth data, it's going to be two very different things. But just know if you see this kind of zigzaggy thing that's all over the place, you're probably looking at some error propagation issues. Okay, so acceleration, we'll try it from the original data. So here's our change in velocity divided by change in time. And then we'll do the same thing with our smooth data instead. And figuring out the slopes of lines and areas under curves, that's pretty much what calculus is. So this is sort of a numerical way to do calculus. Last, I'm going to go ahead and highlight these guys and add in a graph for them again. Okay, so here is the acceleration. If we started with the polynomial cubed, that will go squared for velocity, and mx plus b, it'll be linear for acceleration. And if you've had calculus before, you'll recognize that cubed, squared, linear progression. But no, if you haven't had calculus, there's what you learn in math will be applied later on, and you'll use that. And difference between position, velocity, and acceleration, that is, but then afterwards, kind of look at your graph. So you're speeding up, and slowing down, slowing down. So that's your velocity, speeding up, slowing down. And your acceleration that's going to create this, acceleration is the slope of your velocity. So you have a larger slope. Up here at the top, the turnaround, that's going to be a 0. And then negative slope, negative acceleration. So study these graphs, play around with the PhET simulation, and the more familiar you are with these, because you'll see them in multiple classes, and you'll also see kind of some of these things in calculus too, and that's some error propagation too for you. Okay, let me know if anything gives you trouble or is confusing with that.